Hi, it is 1:30, so let's begin. My name is Sunil Agarwal. I'm a program manager with SQL Server team. I'm here to present about in-memory OLTP engine. This engine has been in development for the last 4 years, and I'm really excited to see that this is going to be part of the next release. With me, I have Rick, who has deployed in-memory OLTP engine in their production environment, and he's here to share his experiences with that engine.
Yeah, hi. Don't want to keep you with my stats too long. My name is Rick Kuchar. I work for bwin. As you can maybe tell from my accent, I'm not a native speaker in English, so sorry. I said yesterday already, if you don't understand me, just give me a sign. I'll try my best to rephrase things. As Sunil already said, I've been working with in-memory technology for a while, so share some experience with you. Please switch off your cell phones if you didn't do that already. I forgot to bring my aquarium because normally if a cell phone rings, I try to submerge it and get it over with. So don't tempt me. So no.
So on the English as a second language, even my English is a second language, so I'll try to be slow and use the same protocol as Rick just talked about. So this is an overview session, and there are 2 sessions that I will do, one tomorrow and one day after, which go into a lot more detail. So my goal of this talk is to get you the secret sauce that creates Hekaton or in-memory OLTP engine that gives us, in many cases, 30x performance. 30x is huge because a lot of people will be happy if they get 20% gain, right? I mean, we are talking a order of magnitude gain. And my goal is, after we are through with this 4-slide overview, just 4 slides, you will understand at least the rationale and the reason why we are getting. At least you see the potential. And I think that's my goal. So as I said, we will be working on this Hekaton. I'm going to use the word Hekaton and in-memory OLTP in a very interchangeable way because for the last 4 years, we have been using Hekaton. And only last week, the official branding is in-memory OLTP, so it takes time to switch from Hekaton to in-memory OLTP. So when we wanted to develop in-memory technology, we wanted to have a relational engine that is ready for the next generation. When I say next generation, it is important because when you look at popular relational database systems like DB2, foundation was done with System R in 70s, Oracle, early 80s, Sybase 84, then the company was formed, and Microsoft got a version of Sybase and they evolved on that, right? So when those systems were designed, the hardware was different, the business was different. So we wanted to build something that is right for the technologies and the trends that are available today. So it's a leapfrog. So to provide that incentive, we will first look at the business trends, what is causing it, and then how the new generation engine that we have with OLTP, in-memory OLTP, how we are using those trends to provide a very high throughput and low latency kind of performance. Another thing is, this is not a new engine in the sense this is not a new product. We have integrated that Hekaton in-memory OLTP engine inside SQL Server. So it is SQL Server from your perspective. It's just a new engine sitting inside it. And then Rick will go into their experiences with in-memory OLTP engine, how they used it, what the challenges they had from their business, and how Hekaton solved those challenges. So when you look at the business trends, what we are seeing, and this is not a news to any of you, what we are seeing is there's a constant requirement to lower the latency for their applications, and we are seeing a very high demand for throughput, right? So I'm going to take a very simple application that all of us use or experience that is the credit card transactions. Imagine this, you go to a grocery store or any place, you swipe your card. It has to authorize, right? It has to validate it is you, it has to authorize, and then it has to complete the transaction. And that has to be done real fast, right? Because otherwise, I mean, you cannot keep on waiting. And there are if not millions, hundreds of transactions going on at the same time, because credit card company has to process tons of transaction processing, and it has to be done real fast. So that's a example. The second example, which is a bit new, is online gaming. Now think of this, right? You are watching Super Bowl, and a field goal is about to be kicked. Now imagine if you can place a bet on it, whether the field goal will happen or not. To make that happen, it has to be wicket fast. I'm going to use a term that Rick uses all the time. It has to be wicket fast. I mean, to be able, the field goal, I have to place the bet. Blade has to be stored in the system before the kick is done, right? Otherwise, what's the point, right? Not only that, you want to have lots of customers to place the bet at the same time. So the requirement is it has to be very quick, and it has to support high amount of throughput. So that kind of applications are possible today. And as Rick will tell, is with Hekaton, they're able to meet that kind of workload. So this is actually very exciting for us. So those are the business trends or the business reasons why we said we have to go to the next generational SQL Server. The hardware trends. There are three trends that are very critical for us. First, we have systems now with tons of physical memory. I mean, how many of you have boxes in your production environment, say with over 128 gigabyte of physical memory? Just raise, right? I mean, this is huge, right? I mean, like people have that kind of physical memory available in the box. So how do we use that kind of physical memory to deliver better performance? The second trend that we are seeing is the clock speed has plateaued at 3 gigahertz. It is not going beyond that. Now imagine if you go back to 90s when the Pentium chips were coming out from Intel. It started, I remember, 133 megahertz. And if you wanted your program to run faster, all you had to do was wait for the next Pentium chip, right? The frequency will be doubled, your performance will be that much faster, right? But now the frequency of the clock is plateaued, so it's not going to go up at that level, so you cannot really get any free performance. So in that case, what can you do? I mean, if the clock speed is not going up, so there are two ways to do it, right? Either clock speed has to go up, which is plateaued. Other way is, can I execute my program with fewer instructions? So for example, if my program took, I'm just taking a very simple example, 10,000 instructions to execute, right? And it takes whatever time it takes. If I reduce those instructions to say 5,000, that means my program will complete in half the time. Right? That's another way to speed up your performance. So that's an angle that we have taken with Hekaton. And the third thing that we have seen, I mean, this is the Moore's law, that the transistor capacity is doubling every 18 months. So what we are seeing is you are getting boxes and the CPUs with a lot more cores. I mean, it is not uncommon to see machines with 64 cores. One of the things that I was looking at before I came here, you can buy a 24-core machine with 256 gigabyte of physical memory with SSDs for around $12,000. I mean, this is huge computing capacity that you have for $10,000, $12,000. Imagine this, right? I mean, how much money you have to pay to manage systems and things like that, right? So this is not a huge amount of money. So those are the trends and the business requirements that fed into in-memory OLTP engine for the next generation. So what Hekaton is, it's a high-performance OLTP engine that is optimized for in-memory data. I'm just going to tease this apart. So it is high-performance OLTP engine optimized for in-memory data that can deliver the high performance and throughput for today using the modern hardware trends, memory, number of cores, and things like that. So what you have now with in-memory OLTP engine is a next generational engine, if you will, for SQL Server. Now this does not replace SQL Server engine that we have. It is going to be together. So if you look at the SQL Server instance with SQL 14 that comes out, the Hekaton engine is part inside, embedded in the main engine. So let's look at the four pillars that we have for Hekaton. The first, I'm just going to go, if you look at the bottom, it is hardware trends in the TCO or the business requirement. The first thing is the declining price of physical memory, right? Now, as I said, when the databases were designed at that time, the size of memory was much, much smaller than the size of the database. So how did we do it? What they said was we will break the data into pages, right, and only bring those pages that are being accessed. So essentially what you're doing is at a given time, you are bringing only a subset of the data into your buffer pool, right? Those are the hard pages. And there were like caching policies which will figure out which is the page to kick out, that kind of buffer management, right? So that was essential. Now imagine this, right? You have a database which fits in physical memory, okay? Let's just take an example, and it is page-based. So now everything is in physical memory, and I ask a question, find me an employee whose ID is XYZ, and I want to know his address, right? So what you do, you say, okay, I'm going to query is select employee address from employee where employee ID is so-and-so. In general, what you will have is an index on employee ID, right? So assume the data is in physical memory, right? So what happens is SQL Server will say, I'm going to use this non-clustered index on employee ID. So you go and it needs to get the page, which is the root page or the top of the index tree, right? It gets the page. Then to read through the page, it has to latch the page. Then it has to search within the page where is the next level it has to go to, right? So it latches the page, finds where the next page is, right? So it goes to the next page. It does the same operation, latch the page, finds the next page, and next page, and next page, right? Now imagine this, if this index was 5 levels deep, you have already gone through 5 pages, all in memory, one by one, and for each page you were latching, you were searching, and so on, right? Now, it was a non-clustered index. It is possible, and it is very likely that address was not a covering key. So now, because in SQL Server, the non-clustered indexes are built on clustered index, now you have to go through the clustered index, right? Let's say that's 4 levels deep. So essentially what you have done is, you have traversed 9 pages to get to the row that you want, right? Even though the data was in physical memory. Wouldn't it be nice if I could have a hash index, for example, which is in-memory index, and all I have to do is I hash on employee ID, it goes to the bucket, and gives me the pointer to the row that I want. So just doing that, I can get my data fast, right? So the way I think about SQL Server, if it was like traditional disk-based tables, okay, let me just clarify. When I say disk-based tables, I mean the tables that we have today in SQL Server. So in this case, if I have all my disk-based tables in memory, I would say that your database is in memory, right? Nobody argues that. Your database is in memory, but it is not memory optimized. Why? Because I just described to you, even though everything is in memory, I'm still going through a lot of hoops to get to the data I want. So what we have with Hekaton or in-memory OLTP engine, we have optimized the code to exploit the fact that the data is in memory. Right? So the data, Hekaton requires data to be in physical memory. What it means is that there are no pages, there is no buffer pool, okay? And we have specialized indexes which can exploit the fact that the data is in physical memory. And the fourth thing is the storage that we have for in-memory data is a bit different because there is no pages. We store in a very different way. And our storage, it will be a lot more detailed to say how it is, but it is stream-based. Just think of logs, right? The storage for Hekaton in-memory table is also like sequential access. So those are the things we have done. So that's why we are saying that Hekaton or in-memory OLTP is optimized for memory. Okay? Now, second trend was the clock speed is not going up, right? So clearly the thing was we have to figure out a way to take fewer instructions to execute the same logic, right? So if you think of SQL Server, right, you have a stored procedure, you optimize, you compile, and that's a stored procedure, right? But think about how we execute the stored procedure. When you compile a stored procedure, it compiles it into higher level operators. So I'll give a simple example. You have a sort, you have a joint query with a sort, right? So what happens is the top level operator will be sort, fed into by join, and the join is being reading tables, two tables, right? Two scan. The sort, join, scan, right? So there is a engine, the query execution engine, that is opening these operators and executing the whole logic, right? So this is a interpreted execution of the T-SQL stored procedure, right? So what we did with SQL 14 is something pretty amazing. What we did was we took the SQL stored procedure, transformed it into a C program, and compiled through Visual C compiler into DLL. So now what you have is not interpretation of your logic through query execution. You have the machine code as a replacement for that stored procedure logic. Now with that, you can execute the stored procedure in much less number of instructions. So by doing that, even though the clock speed was not going up, but since we reduced the cost of executing the stored procedure, we are seeing much faster execution time. In fact, we did an experiment where we took the SQL database disk-based tables in memory, and we ran a transaction which is a OLTP kind of a transaction, and we found it took like around 1 million instructions to execute the transaction in a traditional SQL database, which we said everything in physical memory. The same transaction with all these optimizations took around 40,000 instructions. So basically, we are getting around 30 to 40x improvement just by reducing the instruction count. Okay? So that's number 2. Number 3 was we have a lot more cores. Now, SQL Server scales very well. I mean, we have, when we came out with SQL Server 2008 R2, it was scaling well up to 256 cores. However, there are some application patterns that they do not scale well. I mean, some of you might have seen the problem of scaling when you have multiple transactions inserting rows on the last page. Has anybody seen that kind of issue, experience? Last page insert, latch contention? I've seen a couple of hands, but it is a common problem. Or if you have a small table and there are a lot of transactions making changes, so they will hit the same page. The basic latching problem is that in a page structured system, if you have multiple rows from different rows for the same table which are not related to each other, but they just happen to be on the same page, if you and I are updating the row on the same page, even though those rows are not related, I need to latch the page to access my row, right? So I get a lot of latch contention. So because of that, your applications in many cases do not scale well. So what we did with Hekaton is, number 1, we got rid of page structures, right? So there's no paging anymore, so there's no latching. And we use lock-free structures. So there is no locking. It uses optimistic concurrency control. By doing that, we are able to remove a common scalability bottleneck that we see with applications. So now what you have with Hekaton is we have optimized the code for in-memory access. Hekaton requires the data to be in physical memory. We have reduced the instructions by compiling the stored procedure into C code. I mean, that's pretty amazing. And we have removed the scaling bottleneck by removing the latching and the locking conventions, right? So those 3 are the key technology things that we have done with Hekaton. And with that, we have been able to get huge amount of performance gain. Now, it is easy to say, you know what, this is a new engine. I'm going to release a new bits. I mean, this is what customers should use. But no, what we wanted to do was we wanted to leverage a lot of infrastructure that SQL engine provides to us, right? So we embedded the engine into SQL Server. So it is an integrated part of SQL Server. So what it means is you have a very familiar set of tools available to you. Nothing is new. You can, if you know SQL Server, you know Hekaton. It is that simple. You have the same manageability, same administration, backup, restore, everything just works the same. So if you have a database with Hekaton, you use a backup, it will get backed up. So there is nothing new to learn. So that's another important thing. That's a new, not a new product. It's pretty much the same thing. So now the question is, how do I, okay, this is Hekaton engine. I say CTP1 comes out and you will download the bits. The question is, how do I use it? How do I migrate my application to Hekaton, right? So the next slide is actually going to that. So what I'm showing here is your existing SQL application. So in this case, what I'm showing is you have, say, 3 tables. It's a very simplified model, 3 tables, and each table has an index. So index shows here, like you were seeing the index right there in the index. And at a given time, you are accessing your workload. A subset of pages from each of these tables will be in the buffer pool, and this is what it is showing here, right? Right? So this is pretty much the familiar model you have. And then you have stored procedures and ad hoc SQL queries that are using these tables, right? That's your application. Now you know that your application is not scaling well or not performing well. What can you do, right? So SQL Server 14 will come out with a tool that can profile your SQL workload and can tell you these are the tables that will benefit the most if you migrate them to Hekaton. It will tell you that. And the reason it knows, because it knows which tables are hitting latching issues, which stored procedures are taking a lot more CPU, right? Because if a stored procedure is taking a lot of CPU, if I can compile that into C code, I'll be better off, right? Okay. So the tool gives you that information. And that's pretty amazing. And now what you do is, with that information, you say, okay, it identified some tables. In this case, it identifies table T1 and T2. So what you do is, okay, I got table T1, T2 identified. I'm going to migrate those tables into in-memory OLTP engine. And what this migration is, essentially what you do, you say create table T1 with memory optimized option on. It's just as simple, right? We create the table, you migrate the data, insert into select star from source, the data goes there. Now you have your table T1 and T2 in-memory OLTP engine, right? And then you remove the table from the source. So now, after this migration is complete, what you see is the T1 and T2 is not sitting on the right side, right? It is sitting in the in-memory engine. So a few things to note. Number one, your database, the SQL database, is still the same. You have three tables, T1, T2, T3. It just happens that T1 and T2 are part of in-memory OLTP engine, and T3 is still the disk-based. So from a database perspective, you did not have to break your database into two databases. Same database, some tables in memory, some tables are disk-based, number one. Second thing that you see is that in my storage, I have a new kind of storage for in-memory tables. It is not the old file group that I had for my data. And the reason is we store data very differently for in-memory tables because it is not page-based. Okay, so that's that. Third thing which is very important is that we don't persist the index. We do not persist the index of in-memory OLTP tables. Okay? What we do is when the table is loaded in physical memory, for example, I shut down my server and I started, the data has to be loaded from disk, right, onto the physical memory, right? Because unlike disk-based tables where data stays in the disk, only fetch when you access that, right? But when you start OLTP engine with in-memory technology, you have to load the data. When the data is loaded, we build the index on the fly. Okay? So we only have the metadata for the index, but it is not loaded, it is not persisted on the disk. So now the question is, I got the data, how do I query it? So we provide two modes to query it. The first mode is you can run your SQL logic as before. All you have to do is move your table to in-memory. I'm going to use the word memory optimized. Make your table memory optimized, and your existing stored procedures will continue to work as before, except in this case, they are accessing memory optimized table. And the benefit that you get is, because it is memory optimized, it is not doing latching for that table. It is using optimistic concurrency control. No changes to the application. All it did was move the table. Okay? So that's one way. And we call that way as interop. What interop means is that I can have a query that is using both memory optimized tables as well as disk-based tables. Right? So if I have a joint, for example, between table T1 and T3, it is possible I move table T1 to memory optimized like I had done here, and T3 stays as disk-based. So I can still do select star from T1 comma T3, whatever conditions. It should just work. So this is what we call as an interop, because it is doing a query across disk-based and memory optimized. Right? So this has helped us to make the application migration very easy, because many customers don't have the luxury to change the application. Right? So all they did was they just changed the table from disk-based to memory optimized, and the application continues to work. In one of the demos, I don't know how many of you were in the foundational session yesterday. Just show me anybody was in the foundation. Some of you, right? So we saw, just by moving the table, we saw 6x gain. And the reason was we were able to see 6 times the gain because they had heavy latch contention. All I did was I moved the table to memory optimized. The latch contention was gone. And because of that, I was able to see that. You have a question?
Yeah. Does it make sense to move descriptor tables over there, or does it make sense to leave those in the main?
Ask me, sorry.
Does it make sense to move like the descriptor tables?
Descriptor tables.
Yeah.
So I think the question really is, how do I know which tables to move? I made a very simple statement that we provide a tool which will tell you, you just close your eyes and you just believe that, right? But the key point is, when we decide which tables to move, we are looking at the tables. Number one, is it getting a lot of latch contention, right? If the table is not getting latch contention, you have little benefit of moving it. I mean, even though it's a good idea, but the key point is the tables that are going to benefit the most by Hekaton, we recommend that. So the descriptor table is not having any performance problems. There's no reason to move to Hekaton, right? So that's that. So that's the interop way. Now the second thing that we talked about was compiling the stored procedure into machine code, right? So that we call as native. So what it does is, as I said, once you have migrated the table, now you look at the stored procedures and you say, you know what, this stored procedure is taking 30% of my CPU because it is heavily used. Can I just move that stored procedure to native? So what you do is you can say, okay, there's a different syntax for that. All you need to do is I take that and I'll compile as native, and it gets compiled into machine code, and you can get much better performance. Now the limitations, there are some limitations, right? Think about that, right? T-SQL is a huge language. Now creating code to convert a T-SQL procedure into C is complicated, right? So what we have done is we have focused only on the constructs that are common in OLTP operations. Of course, we have to do select, delete, insert, update, those common operations. So we have done that, and then all accesses to tables inside the native stored procedure is only for memory optimized table. Okay? So what it means is, if I move a stored procedure to native or machine optimized, and it is accessing table T1 and T2, those two tables have to be memory optimized. You cannot have a stored procedure that has memory optimized and disk-based table. However, in the interop mode, we support both. So let me just say that again because it may get confusing. So in the interop mode, you can access both memory optimized and disk-based tables without any changes, right? Everything works. And it is going to be at least as performant as you had before, but most likely better because you're choosing the tables that has latch contention, right? But if you want to move stored procedure to native, then you have to make sure the tables that are referenced by that stored procedure are both memory optimized. Okay? Now these things together, as I said, we have been able to get gains, and this is something that I showed in the demo, like 25x gain. I mean, this is not something just demo. I mean, we have Rick, he will talk about his application. This is something we have seen in production. And we have been working with many, many customers along this journey, and I'm seeing many customers are able to get like 7x, 8x kind of gains. Now, it looks less compared to only 5x, but I mean, 8x gain is like tremendous, right? Yeah. So that's the kind of technology we have. With that, I wanted to hand over to Rick. He can share his experience. We have been working with Rick since 2009, if I'm not wrong. Just when the Hekaton project started, we have partnered with Rick, and the benefit for us has been that Rick's team had been providing us the feedback because it's good to design in our development environment, but it's good to have customer validation. So we've been working very closely with Rick and some other customers to help us make sure we are on the right path and we are solving the right problem. So with that, Rick was the first team to deploy Hekaton in production. I mean, this is amazing. I mean, Hekaton is being CTP1 now, but Rick's team had benefited so much with this technology, they deployed in production. And he's going to talk about that. This is a question.
Suppose you have a table right now as 100 GB and your memory is 128 GB. Over a period of time, your table grows to
That's right.
100.
Right. So the question is, actually a great question. The question is, unlike SQL Server, right? I mean, if you had a buffer pool of 64 gigabyte and your table grows to more than 64 gigabyte, no big deal. We only bring the pages that you need into physical memory. In the worst case, your page life expectancy will go down the tube, but at least data is there. What we require from Hekaton perspective is you have to guarantee that is enough physical memory for your tables, right? So the key things to note is, number one, you do not have to move your full database into Hekaton, right? We have to be very choosy about which tables make sense to move to Hekaton, number one. Second thing is, if the table is like 100 gigabyte and you have physical memory of 128 gigabyte, it's almost like thinking, right, you have a database of size 100 gigabyte and you have disk of 128 gigabyte. What you do is you buy more disk, right? So what we have is, in that case, if you want to take advantage, you have to buy more memory. But remember, I was talking about you can get a $10,000, $12,000 box with 256 gigabyte of memory, right? So that's not a big problem to solve. That's right. That's right. So the real question is, I mean, those kind of gotchas are there even today. Like, for example, somebody opened a transaction, went for lunch, your log doesn't get truncated, right? So those things you have to monitor. We have the monitoring tools available. If somebody is doing that kind of stuff, you can kill it. So, but you make a very good point in the sense, it is possible that Hekaton, in a very, ad hoc system where somebody just inserted millions and millions of rows and eat up all the memory, what we are providing is tools so that you can constrain how much memory Hekaton engine can use. We are providing all those things and a monitoring capability. So it is true, like any DBA, you have to monitor your systems to make sure that system has right resources for the workload. But the key point is we have to make sure the physical memory is available for the table that you have in Hekaton. Let me take a question here. I'll come. Yeah, question.
Can you touch on the log architecture because you need pretty fast storage?
Right. Right. So let me do one thing. I'm going to take 5 more minutes and then I'm going to give it to Rick because we have to. This is actually a very important conversation. So one thing which we have done is, right, when you look at this picture, on the left, rightmost left, that's the memory optimized file group, right? So if you think from SQL Server perspective, it is file group, right? When I do backup my database, it backs up my primary file group, which is disk-based tables, log backup, like log disk, as well as the memory optimized. So the backup command works as before. If I do a log backup, so what we have done is, it is the log of disk-based tables and memory optimized tables is integrated together. So when I do log backup, I'm backing up not only my changes to the disk-based tables, I'm also backing up my in-memory tables, right? Now the question is, if I'm going to give you 10x better performance, that means I'm generating 10x more log, assuming everything was DML, right? But I would imagine there are a lot of queries. I mean, there are like 50% read and write. But point is, right, I'll be generating more log, right? So how do we manage that, right? So clearly, if your bottleneck in your performance is that you're not able to write enough log, you have to upgrade the disk, to get better, right? You can go to SSDs and things like that. Second thing that we have done, which is actually very, very important, number one, we do not persist indexes, right? I was talking about we do not persist indexes. That means if you think of a table today in disk-based, let's say you have 6 indexes, I insert a row, I have to log the row, data row, and I have to write logs for 6 index log records, right? But with Hekaton, all you have to do is write 1 log record for the row, right? So we have reduced the logging. Second thing that we have done, which I will go more detail into my next sessions, is we write the log only after transaction has been guaranteed to commit. So this is very different compared to SQL. And this gets a little geeky point, but let me try that. So in SQL, what happens is, as you begin transaction, you update a row. You have not done the commit. What we do, we write a log record, right, and change the page. What we do in the log record, what was the value before and what is the value after. And now if I want to roll back my transaction, I need to go back to the previous value. If I go forward, then I'm set, right? So we are writing those log records. In Hekaton, we only write the log records at the time the transaction commits. That means we are guaranteed the transaction will not roll back. So we do not write undo log record. We just write the redo log record. So what I'm trying to say to you is we have optimized the way we do logging to support that. But it's a great question. I think there were more questions. I'll take 2 more questions and I'll give to Rick, and then we will take more questions after the presentation. I'll go here, then come here. Yeah. Correct. So great question. I mean, these are some of the things we thought about. What happens? See, first think about this, right? When you have a table, very large table, typically people have partitioned the table, right? Only the most recent partition or partitions are most active, rest is dormant, right? So what people are saying, can I create a table, partition table, so that older partitions live in SQL, disk-based system, and the new partitions live in as memory optimized, right? So unfortunately, at this time, we do not provide partitioning as a feature for memory optimized tables. So what you could do, you can create a view. You can basically do a partition that you used to do before 2005 came out. You have a SQL table, same schema as Hekaton table, create a view. So you can do that way. And there are some techniques, but I think the point is that there is no automatic moving of data from memory optimized to disk. So you have to manage in a manual way at this time.
How does Hekaton relate to column store indexes? Would it still make sense to use them once
Right.
Hekaton is available?
Right. So the column store is more geared towards data warehouse scenarios. What Hekaton is providing is in-memory OLTP. So in that sense, they are, but you can have an application where you have some tables Hekaton, some table Hekaton in memory optimized, and some tables sitting in SQL disk-based system, which could be column store. So they play together, but they're addressing very different scenarios. So I'm going to do this, if you allow me. I'm going to stop here, let Rick take over because he wants to describe his experiences with in-memory OLTP engine for their production environment. And we will take questions after that. And me and Rick will be here for a while, take all questions that you have. Thank you.
Okay, so let me take over this with our experience with Hekaton. And I'm always open also to answer questions. You'll just have to live with the fact that I answer them a little shorter than Sunil normally does. Very well. What I want to give you is a little overview of what we did. The architecture we had before we had Hekaton and after we had Hekaton, including the problems that we had that more or less forced us to do what we did in this early stage. Talk a little about the performance numbers. And of course, the maybe most important part for you thinking about this thing is how did we migrate it and what were the challenges during the migration. The thing that I'm talking about, the application that we first used in the area of Hekaton is a ASP.NET Session State Server. And it really, literally, when the guys from Microsoft approached me and said, hey, we have this cool new idea of a memory-optimized database, this was the first thing I pointed at and said, that's the thing we need it for. It took me 1.5 years to actually get the Microsoft people to jump on board of this, because after all, the Session State Server is a Microsoft product. But finally, we get it. So what is a Session State Server? For those of you who are not familiar with it, if you have a website with multiple web servers, and we are getting more and more web servers on the web farm, scale out makes it possible, then you have certain amounts of data that need to be coordinated between user requests. So for example, if you open bwin.com, our main website, it actually generates 50, 100 requests just to display the first picture, the first page, because of AJAX requests, because of the pictures on it, because of framing and stuff like that. But still, all of those belong to the same person. So if you want to have the user that is logged in have special content everywhere, we need to transport the information about the user from one request to the other. And those requests are not hitting the same web server. So you have a central store somewhere that needs to coordinate. I'll show you what this looks like in a little while. The key point there is everyone that has a request on the web server needs to go there and go back. So a delay on the session state server means a delay on the website, direct impact. On the other hand, this is very short transactions. This is a burst that normally takes only milliseconds. So this is nothing like a data warehouse query that takes forever. You have small data size. I have to be a little careful because there's something I'll say later on that contradicts this to a certain extent. But the point I'm making here is the entire database for our high-load website is not more than 20 or 30 gig at most. And one thing that was important for me, and Sunil did not mention this entire area, this data is transient. If we lose it, yeah, so what? The only thing we lose is that the user was logged in, so he might need to log in again. So this is nothing that is really highly critical data. Although I have to say that we also use Hekaton nowadays for things that have highly critical data where this is not true.
Right. So Rick, if you allow me, let me elaborate on that point. So what we provided with Hekaton are the tables which are fully durable. So when people think of in-memory, they think, what happens if system shuts down, crashes, do I lose my data? Answer is no. It is fully ACID. I mean, we log, we store, everything is taken care of. However, we provide another option, which I did not mention, is non-durable option. So you can have an in-memory table, but you can say this data is not durable. Okay, what it means is I insert the rows, they're not logged, they're not stored on the disk. And this is a very important concept because in ETL scenarios, you want to load data from external source into SQL Server to do some massaging before it is shifted to the final destination. You can use non-durable tables, memory optimized in a very transparent way. So that's actually a very powerful tool we have. And this is also very useful for scenarios where the data is transient, like the session state server that Rick is talking about. Let me give back to Rick, and then we'll come to that. Yeah.
My question is related because Windows caching services also provides the solution to this problem. Have the session state server.
Yeah, so the question is about Windows caching services. I'm guessing you're talking about what was called App Fabric in the past. So we tried App Fabric as an alternative to Hekaton. Just let me say, it doesn't scale that well once you hit a certain point, because when you start to scale out a Dcache like this, the coordination work that you have to do between those cache nodes gets in the way at some point. But yeah, there is an alternative to that. It just also has its limits. When I talk about the numbers, I can side note you the ones that we get from App Fabric. Okay, so what does the architecture look like? I gave a quick overview already. You have a web server farm and one central session state server. And this is normally becoming the bottleneck. So when a request comes into this, if I get my request, thank you. The first thing that happens is that the web server does a request to get the session from the session state and places a lock on that session. This lock is not a SQL Server lock. This is an application side thing that is just an update flag. But this lock then stays on while the web server does the computing of the web response. After the computing is finished, so the website, the web page that it's going to send out is already finished on the web server, then it updates the session, and only then gets the lock released from the system. So not only was the throughput a problem in this thing, also the response time, even if it's just milliseconds, could in a web page that have 100 pages to load get you to almost a second delay just because of the way a session state is working. So how did we solve this problem? Well, let's call it scale out of the poor people. We partitioned our web page more or less, having one for each country, and every country has its own session state server, which in the end, with high availability and disaster readiness and everything that came with it, let us end up with about 18 session state servers to maintain. And even then, the big one, bwin.com, was so big that we started having problems with it. What did we do with Hekaton? Well, the picture is not exactly impressing. We just reduced everything to one because one is now big enough and can handle everything we have with still some room to spare. And we now push all the web servers to the same thing.
This is pretty amazing that 18 backend servers were merged into one, and it can handle the load.
Yeah. And this is not a Superdome or some kind of a $1 million box. The session state server that we use for all this costs less than $30,000. So let's talk a little about the Hekaton effect. As I already said, we only need one server now to service all web farms. Less license, less power consumption, less space, less management overhead. You have less workload on the DBAs because if you want to change something, you only change it once. You don't have a problem with consistency between the servers. Everything works perfectly on one single box. Hekaton does scale linearly. And that's the big difference that we saw from the previous implementations. With SQL Server, you have the latch contentions that Sunil talked about, and at some point, those would just take over. There was a tipping point, and everything would slow down. I have not seen slowdown in Hekaton so far, up to the point where my servers just maxed out on CPU.
Right. So, Rick, I think if you allow me, I just want to emphasize this point. This is actually so critical. Not only you got performance gains, you reduce the number of servers you need for your workload, reduce licenses, reduce management cost. I mean, it's like a lot of benefits, right? And that's what you saw.
Yeah. Additionally, Sunil already said that when you do native compiled procedures, you can reduce the number of CPU cycles that you need. Actually, even if you don't use native compiled stored procedures, you can tremendously reduce the amount of CPU cycles you need, because even in interop mode, Hekaton is still faster and better. To put some numbers on that, before we had Hekaton, the session state server gets, in the way that Microsoft delivers it, up to 10,000 requests per second. And as you saw in the picture before, you have one get and one update request, so 10,000 means 5,000 web requests. With some tuning and some fuzzy things in the end, you get to 15,000 batches per second, and then you end up with latch weights, and there's just no way around. With Hekaton, on a 4-socket box, we ended up with 250,000 requests per second. So compared to the original, this is a 20x increase, or 13x if you, 15x if you take it from our optimized point of view, with doing almost nothing. And the critical thing on that is we did not touch the application, we did not touch the web server, we just changed something in the database. And it suddenly, poof, started to work. And then with 250,000 batches per second, the 4 sockets just went to 100% CPU load and maxed out, together with my 10 gigabit network adapter, by the way, which also maxed out at that point.
Right, and this is like a real application, and it's a huge number that you saw.
Yeah. Okay, now I think I did enough marketing for Microsoft. And I'm not here to tell you everything is nice and warm and sunny. We have a lot of problems too with this whole implementation. Hekaton, although it looks the same, I would have loved to show you a little bit of the syntax, but Sunil didn't want me to. There are still some things you need to think about of this. So when you convert a table, pretty much everything you do is script out the table and add a with memory optimized is on in the end, plus minus a little funny stuff in the middle. The problem is not everything works the way it is. Hekaton, as we see it today, is a typical version 1 product. It is built for the things that are important. It is built for the things that give you the most gain, and that was the focus and the goal of this. With me being involved with this for quite a long time, it actually has pretty much everything that I need. So I'm the lucky one. You have to live with what I needed, so you're not so lucky.
So on that, I think we have been working not only with Rick, which is an important partner for us, we've worked with a lot of customers. So hopefully it is more than what Rick needed.
I hope so too. Okay, so to point out one thing, not all data types are supported, especially with our environment. A session state server has an image column, which basically is a binary large object. Not working that way. Hekaton is limited to have 8K per row, so everything over that does not fit into Hekaton. No nvarchar max, no varchar max, no var binary max, nothing like that. The first idea I heard from Microsoft to that was, well, you store everything in Hekaton and you put your blob in a normal SQL table. Yeah, well, if the blob is the thing that you really touch every time, not a good idea. So what we did is, and once the bits are public, I'll get this on my blog and post it for everyone who needs it. We built a Hekaton version of a blob store, basically splitting up the blobs into 7K chunks and pushing the 7K chunks into Hekaton and transparently putting them back together when we put them out to the program. Also, CLR types are not supported, spatial types are not supported, and some others, I don't know. I
Right.
don't
So
remember.
let me interject a little bit. So our focus has been the OLTP workload. The CLR and the spatial data types are not commonly used in OLTP. So yes, we are not really supporting the full surface area of SQL Server, Transact SQL. Focus has been that, but yeah.
The second thing is when you think about memory compiled procedures, native compiled procedures, it has the same issue. Not everything is supported in a native compiled stored procedure. The things that I pointed out here is we don't have sequences, we don't have identity. There are also some kind of functions that are not supported. Sunil already said you can't join a non-memory optimized table in a native compiled stored procedure. So there's a lot of things that you need to think about. To be fair, the 250,000 batches per second on my session state server are made 95% without native compiled stored procedures. Why? Because we don't need it. It doesn't get much benefit. Yes, please. Yeah. So the statement here was if everything is in memory, then you don't have to worry about interop, and that should not be a problem. Yes, that's right. If you put everything in memory, this is not a problem, but not all scenarios permit you to have everything in memory.
Right. So
let me finish the sentence. In what you think asked before to put those fact tables in memory as well, that's the reason to do it, and that's the reason why we did it in some other scenarios too. So
right.
no, please.
So I think we need to differentiate between everything in memory versus native, right? So those are two orthogonal issues, right? So your data is in memory, right? Memory optimized. You can access the data or the table through interop or through native, okay? What native buys you is it is compiling the stored procedure into machine code. So the number of instructions needed to execute the stored procedure is order of magnitude lower. So what happens is the CPU cycles that you need to execute the stored procedure goes down tremendously.
Yes, please.
Just quick on the native stored procedure. The access path, does that get created at file top when you create the C code? And if you have to write anything new to handle changes to that query plan that might happen?
So the question is along the lines of changes to the query plan, does this stored procedure gets compiled? I have not seen the latest versions of that, but
I think it's a great question. This is something I will go into in my session tomorrow. So I think what you're referring to is as data gets loaded into more tables, the query plan could change because statistics has changed. So since the stored procedure is compiled into DLL, how do you update that? At this time, it is not auto recompile. So what you need to do is if the statistics has changed dramatically, you need to drop and recreate the stored procedure. So that's the limitation you have at this time. Yeah.
okay. So let's move on to the next point. Sunil already said, sorry, you have a question?
For these challenges that you described, like sequences and identity, are there plans by the Hekaton team or the memory team to support these?
Right. So when we started off Hekaton, this is our long-term strategy. It is not something that will stop here. So we said we want to get to the market because we want to get customer experience sooner than later. So we said we will focus on the sweet spot for OLTP engine. Okay. So a lot of workloads with whatever we are providing with our SQL 14 will meet the requirements. And key thing to remember is that you're not moving all the tables into in memory, right? So only performance critical. And there are ways to work around these limitations like sequencing and things like that. And I think we can go into that in my next session. So there are plans. We will obviously move forward, improve in-memory OLTP engine more and more. But we wanted to give something to our customers with SQL 14 and iterate on it in the future releases. Yeah.
So Sunil said it right, just to emphasize it from the customer point. Especially with sequences, we had this discussion as well during our beta phases. And it was actually one feature that I stepped down on because it's so easy to work around it that it's not worth sacrificing something else for it. Okay, next point, lock-free. Sunil mentioned this briefly in his slide before. Hekaton does not do locking. Zip, not at all. For database guys, and I think most of you will be database guys, otherwise you wouldn't be here, this is a new concept, a new model. What it basically means is two transactions can access the same record at the same time and can change it at the same time, theoretically. And while in the normal SQL engine, one would wait until the other is finished, they both write this down in Hekaton at the same time, and one of them fails when it commits. This is called the write-write conflict, and one of the transactions will actually break down and roll back at the time of commit. What this means from an application point of view is you need to take care of that. Because in a typical simple scenario like the session state server, where everything is relying on the fact that if you have five transactions at the same time at the same record, and they will just serialize at the record, this is not happening with Hekaton. If you have them really at the same time, 4 will fail, the 5th will go through. The key point, though, is Hekaton is so wicked fast that it doesn't happen. That you, even with 200,000 requests per second, you only have 1 out of 100,000 or something like that that really runs into write-write conflict. Because a Hekaton transaction normally is not measured in milliseconds, it's measured in microseconds. And if you have something that takes 3 microseconds, you're most likely jamming up the network stack before you hit 2 transactions at the same time. So it's a small problem in most cases, but it is one that you have to be aware of. And you have to write a code around that does a retry once this happens.
Right. So,
And this brings me to the last point here. A native compiled stored procedure. One of the things that makes this thing so incredibly fast and so incredibly cool is they're called atomic. You have this block of C code. It goes to one processor core, and it never yields that core until it's finished. It doesn't block, it doesn't need I/O, it doesn't lock, it doesn't need latches. So it runs from the first statement to the last statement without ever getting off that CPU. And then it tries to commit at the very end and fails. The problem with that is that within this native code, and within this block, you can't handle these write-write conflicts because you will not get a chance to. The commit happens at the point when you jump back out of that procedure. So what we normally did to work around this is you take a normal T-SQL procedure and write this as a wrapper procedure for the native proc. And if this native proc comes back with a write-write conflict, you can just call it again. But this is something you have to be aware of. On a side note, even with SQL today, you have to be aware of exactly the same problem. It's called deadlock. But I don't know about your application developers, but mine certainly don't know what a deadlock is. At least they don't know what deadlock handling is. Oh, and by the way, we migrated the session state server with less than 2 days of work in the initial implementation. It's easy.
So this is actually interesting with so many issues that Rick's team encountered. Still, it was not a complex migration.
Yeah. And it's even more impressive when you know that when I did this migration first, half of the features that we have now were not there. Right. So little things like null handling or something like that. Won't tease you again with that. Okay, what was our experience like when we went in production? As Sunil said, we started production use almost a year ago. I think it was July last year or something like that. We didn't have a single crash since then. There's one server, or actually 2 servers for high availability, are just running. And those were at the time almost 1 year before the first public CTP, almost 6 months before the first public announcement that this technology even existed. With still half of the features missing, with still lots of system functionality missing, it's just working. I'm amazed. I've actually never seen a Microsoft V1 product that runs that stable.
So on that, I would like to make this point that yes, it is a new technology. If you think about always on was a new technology, right? So we are adding new functionality with every release. But we are well aware SQL 14 is not V1. SQL 14 is SQL 14. So we are going through amazing amount of testing to make sure the customer experience is what they expect from SQL 14. And Rick's minor recommendation is a testament to that fact. that even 1.5 years ago, the quality was that high. I mean, that's our, I mean, if we mess up the data, we mess up everything, right? So that is absolute needed, yeah.
But to emphasize on that, Always On was also a V1 technology when SQL 2012 came
That's
out,
right.
and it is not as stable as Hekaton is.
Okay, so that's
I'm
good.
sorry.
So we are learning.
My statement still stands. It's the best V1 technology that I've seen so far.
Good.
Unfortunately, not everything is that good. One thing, and we had the discussion already, I think it came from somewhere here, you now have the need to monitor your memory much more closely than you did before. Right now, memory just becomes like disk space. That's it. If you run out of memory, you'll crash your Hekaton instance, and there is no way around that. Just like if you run out of disk space, you will crash your standard database. Also on that line, if you run with persisted tables, so when data loss is not an option, you have to do something with your transaction log. In a real-life high-load OLTP system, and this is the only area where this makes sense right now, you don't have that issue normally, because if you don't have a fast log drive in a high-load OLTP system, you're screwed anyway, and Hekaton can't help you. But I run one of the biggest OLTP systems around. We use Fusion cards, solid-state devices, and PCI Express slots for this, and they can keep up with Hekaton, more or less. So what we see in testing is when I run this fully ACID-compliant, fully rigid, we lose 2 to 3% of the performance using Fusion cards. Okay. The other thing is, and you would not believe that, it caused me headaches during our testing cycles. This thing is so damn fast that you just have no way of monitoring it. What we normally do in testing phases is open up Activity Monitor and see what the things are waiting on. Those things are not waiting. They are gone in microseconds. You don't see what's happening below. The sort procedure, at one point, we miscreated an index. And it was starting to table scan every time we pushed into Hekaton. And it was burning CPU like hell. And it still was gone in 300 microseconds. Too little to measure on any scale that we had so far. So you have to do something else on that. You have to use Performance Monitor. We used kernel rate debuggers to get down to some stuff. I'm still waiting on the end story when SQL 14 comes out on how to actually monitor that. But so far, I always thought the statistics from the query plan cache with its microsecond scale is good enough. I would not be amazed if we would need a nanosecond scale for that, and I'm not even sure if you can measure that accurately.
So one of the things, like Rick's team has been an early adopter to our technology. So one of the things we are doing is adding a lot more monitoring capabilities, troubleshooting capabilities that Rick's team did not have the benefit of at this time. So yeah, so when we come out with SQL 14, it will have a much complete story from the experience from developing the application, monitoring in production, and troubleshooting it.
Let me just add one thing before I jump to the next slide. You have to be aware that when you move into Hekaton, that you change the game in many areas. And just to give you one example, I know it's a little far-fetched for some of you. I ran a test with Hekaton, actually at a Microsoft conference, using a virtual machine. And if you do that wrong, and I'm not talking about overcommitting, I had the whole box for me alone, but the virtual machine could slow Hekaton down by a factor of 1,000 if you are not careful with the hardware below. So things can add up in this pretty quickly if you don't know what you're doing. And while I like the abstraction on some points, and I like the virtualization that we have and everything that comes on top of that, but when you're talking about a technology that gets rid of all those abstraction layers, no more interpretation, no more latching, no more page concepts, really moving down into real memory and moving down to an assembler level code, then such details start becoming important if you really need that. And to say one more thing about that, do you really need it? And that's the question you have to ask yourself. From where I stand, this is not a technology that says, okay, just start converting everything because it's cool and it's there. This is a technology that can give you an edge when you don't have another one. When we started using session state server, there was no way out. There was no way to solve that problem. Now I have one. It's a great one. I love it. But it is made for the things it's made for. It's not the universal tool to solve all the problems that are out there. For that, you have column store index, you have SQL Server, you maybe have App Fabric for some of them. And I promised you to say something about App Fabric on the numbers. Sorry, forgot. App Fabric maxed out at 50,000 requests per second. No matter how broad we scaled it, no matter how high we scaled it up. Okay, with that, Sunil.
Okay. Thanks, Greg. So I would definitely say that Hekaton is a pretty exciting technology. It is. We have seen not only in this application that B1 had with many, many customers who are using Hekaton technology to get even 20% gain. Because the point is, like with the non-durable table thing I talked about, if a customer has a transient data, why do I have to pay my disk storage or the logging? So all I'm saying is that the applicability of Hekaton technology we are seeing in my wide variety of scenarios. Yes, you may not need 20x gains, but the point is, if I can save costs by not persisting my data, or if I can like minimize my scale out solution, right? I mean, instead of like in Rick's case, they had 18 boxes, right? Like suppose I'm running my workload with 2 boxes scaled out. If I can bring that to 1, it's a big win for me because I don't have to manage 2 boxes. So I think it is much wider applicability. On the VM thing that Rick talked about is a very good point, and one of the things we are trying to do is we are publishing white papers on the best practices. So we will definitely have articles, how do you deploy this kind of technology on this kind of configuration. So definitely stay tuned for those things. Yeah, question?
You spoke about OLTP workloads. Suppose you have small databases that are primarily read-only, but the amount of transactions per patches that are occurring are in several thousands per second. Would Hekaton benefit those types of
Right.
loads?
So the question really is that you have read-only database, right? So clearly, in that case, there is no locking contention because everybody is reading data, right? There is no latching contention because when I read the page, I latch for share, there is no latching contention, right? So what you will see typically in those scenarios is you are getting CPU bottleneck because CPU will be pretty much running at the very high speed unless you have IO bottleneck, right? So let's assume that IO issue was not there. You just typically run into the CPU bottleneck. So what we are doing, as Rick was mentioning, that by switching those tables to Hekaton, we reduce the execution code path. So you can execute a lot more. You can increase your throughput just by moving your tables to Hekaton. And if you want to go one step further, you can create native compiled stored procedures, which can take you further, right? What we have seen is that by doing that, the same box, the read-only box, you don't have to scale out to multiple boxes. You could achieve the same kind of a throughput within one box. So that's a benefit. So no latching, no that, but you can minimize the CPU utilization.
Let me add to that. A scenario like this, and we are testing with something like that, does not get you a 10x improvement. You will get 20%, 30%, maybe double throughput with the same box.
With the interop.
Both with interop and native compiled stored procedures. It might, your mileage may vary depending on what your stored procedures do. It is not the huge gain that you get, but if you have a problem there that you don't have the hardware for that, or you don't scale over the hardware, because that can also be tricky in the old SQL world, Hekaton can definitely help you. Question over there.
I understand it doesn't cover the full surface. You mentioned some of the limitations, like row size and sequences, and some data types that it doesn't support, like blobs. How about the full set of SQL specification? Can you write any query against the Hekaton database, or are there limits there?
I think in interop you can pretty much write any query of the specification. I'm quite certain that in native compiled stored procedures you can't.
Right.
There's a lot of things that are not supported in there.
So one of the things we are going to have, once you get CDP1 bits in your hands, it's the full list of what is supported, what is not supported. So first thing I want to clarify, it is not Hekaton database. It's a SQL database. I know you meant that. It's a SQL database which has some tables which are memory optimized, right? So look at that. So pretty much like Rick mentioned, with interop, you have the full surface area to yourself, except we don't support merge command. There are a few commands that we do not support. But again, as I said, we wanted to focus on OLTP workload because that's our sweet spot for this release. You have a question?
Yes. So conversely, about the database where you do long reads, what's the high volatile database where you're doing millions of transactions that you have to store worldwide, you have to log this, but also you want to have a self-maintaining database where you start to archive things that are old, say maybe 6 months or so. So you have a lot of ads, you have a lot of.
Right.
Do you suffer memory fragmentation?
So I think of this. I mean, I want to differentiate disk fragmentation from memory fragmentation, right? So since data in Hekaton is in memory, so there is no fragmentation kind of thing that you see with a disk-based table where, for example, you are inserting rows, right? Things get fragmented. So it's not. Yes, if you're thinking of memory fragmentation, if you are NUMA nodes, I mean, there'll be some impact like that. But no, I think that should not be a material impact from a performance perspective. So what you can do is, if you have like tables that are getting loaded, very highly operated, and your data getting archived, so what you can do is, when you archive the data, you can take data from Hekaton table, move into SQL table or wherever you want, right? And you can keep just 6 months data into that. Those things can be done. No, so there is, I don't see any issue with fragmentation. What I'm going to do, I'm going to take a question here, then come to you, sir.
Okay, so 2 questions. The first one is regarding how big is the database, how much memory we have in there. I think I covered that in the beginning. The database is about 20 gig, something around those numbers, and we have 64 gig in the server just because that was the amount we had in the box. I would not say so. We have another scenario around where we use this as a buffer for inputs for large insert connections where we use 100 gigabyte, 200 gigabyte, 300 gigabyte of memory optimized data. So it scales pretty well up to about 1 terabyte was the biggest in memory that we had so far. The second thing is around using more blocks. As I said, we use a 4-socket box. Based on a Romley chipset. You can use an 8-socket box with that. You start having different issues there because of the way that the processor sockets are linked together, the typical multi-hop QPI issues. We can take this offline because this is a little bit more complex to answer.
So let me.
But I'm here afterwards, so
let me do this. I know this is question answer session now. Some of you are leaving. Thanks for coming. I have 2 sessions, one tomorrow, one on day after. We will go a lot more detail about T-SQL surface area, things like that, and how do we manage storage. So I would love to see you guys there. But anyway, we are here for the question. Thank you so much.